Hey, Patrick, welcome to PyCon.
Thanks very much.
Could you just turn your video on as well?
Oh yeah, sorry. It was disabled in the backstage area.
No worries at all, no worries at all. Welcome back, everyone. We hope that your chosen tracks today have added value to you and your learning journey. Today's sessions have brought out how transformational Python has been across an array of different fields and disciplines. In this vein, our closing keynote dives into how Python is used to answer some of the biggest questions in astronomy and astrophysics. Since the 2021 launch, the European Space Agency, the Canadian Space Agency, and NASA have been exploring the cosmos via the James Webb Space Telescope. This talk will dive into how Python is used to convert raw space data into usable scientific information. It will touch on Python's pivotal role in James Webb's development and showcase some of the groundbreaking discoveries made in its first year. Please welcome Dr. Patrick Kavanagh, an astrophysicist and software developer based at the Dublin Institute for Advanced Studies. He is an expert in high-energy studies of supernova remnants, superbubbles, and the hot interstellar medium. Welcome to the stage, Dr. Patrick.
Thanks very much for the introduction, and thanks for just get this set up, sorry. Thanks very much for the invite to speak at your conference. I'm very, very happy to be here today to tell you about the James Webb Space Telescope, and in particular, Python's role in contributing to some of the amazing stuff we've seen over the last year. So just to give you a very quick overview of the talk, as I was introduced, I'm Dr. Patrick Kavanagh. I'm not actually at the Dublin Institute for Advanced Studies anymore. I very recently moved to Maynooth University in Ireland, where I'm a faculty member now in the Department of Experimental Physics. I worked on one of the instruments on the James Webb Space Telescope for many, many years as a software and calibration scientist. And today, what I want to do is sort of give an overview of the telescope, because maybe not everybody's so familiar with it, what has happened since it was launched, Python's role in both calibrating the data and in the run-up to launch. So everything we used Python for before the telescope was actually launched, so for simulation work and so on, and how that was important for the post-launch process. And then at the end, I will go through some of the highlights, or what I think are the highlights of the fantastic images returned by the telescope over the first year. So with that, just a little bit about the telescope. So as has been mentioned, the telescope was built by a consortium of big space agencies, so NASA, the European Space Agency, and the Canadian Space Agency. It's a very unusual looking telescope, not like the tube-like telescopes people are probably more familiar with. It's an exposed mirror. There's many reasons for this, but the primary reason is that this telescope was designed to detect the very, very first starlight in the universe. And that starlight is very faint. So to collect enough of that light to create an image or to do some real scientific analysis, you need to have a big, big mirror that's capable of collecting as much of that light as possible, but you're still within the constraints of a launch vehicle. Okay. So that's why the mirror looks segmented. It's because it had to fold up to fit into the nose cone of the Ariane 5 rocket that launched it into space. It also has this crazy sun shield at the bottom, which again is very unusual looking for a telescope. The reason for the sun shield is that this is an infrared telescope. It doesn't look at optical light like the Hubble Space Telescope. It sees infrared light, which is radiation we feel as heat. And here's just a little schematic to show what I'm talking about. So the apologies, I can't see my mouse anywhere, but the Hubble Space Telescope looks primarily in the visible and a little bit into the near infrared, which again, as I said, is radiation we feel as heat. But the benefit of looking in infrared radiation is that infrared radiation can pass through obstacles that optical light can't. So looking at the man on the top with the black bag over his arm, the optical light, we can't see his arm because the bag is blocking the light. But if we look at the infrared radiation coming from his arm, it travels through the bag and we can detect it. And this is the kind of principle we're going for with James Webb is that if we want to peer into the darkest corners of star formation process or in the universe, we need to look at this specific type of light because it allows us to see more than has been possible with things like the Hubble Space Telescope. So it was designed to address 4 key science themes. So to answer the biggest questions in astronomy in 4 key areas. And these are the births of stars and protoplanetary systems. So this is where stars like the sun and solar systems like our own come from. The assembly of galaxies, which is how do galaxies like our Milky Way form? Because galaxies like our Milky Way didn't exist in the early universe. We know this from observations with Hubble, for example. So how did they form? We want to look at the very first starlight and how the universe was reionized. So we basically want to know what the first stars and galaxies look like. And we want to also search for perhaps signatures of the origins of life and understand how in other planets and maybe understand how life developed on our own. And this is using very advanced capabilities of measuring atmospheres of planets outside of our own solar system. So in addition to these, the telescope is also a general purpose observatory. It is not designed just to do these 4 specific things. It can look at any object in the sky and revolutionize the science in that area. So it really is a kind of a multi-generational leap forward in capability, but also because it's a general purpose observatory, it can revolutionize all areas of astronomy and astrophysics. So it was launched on December 25th in 2021. Here's a quick video of the launch. It was launched from Kourou in French Guiana in South America at the European Spaceport.
And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
So that was the launch, and it was a very cloudy day, so we couldn't track the rocket very far. But the next glimpse we got of the telescope was after the upper stage had separated and the nose cone was shed, and the telescope was actually deployed onto its course to its current location, which is about 6 times the distance of the moon, orbiting the L2 point. So this is the very last close-up look we got at the telescope. Amateur astronomers around the world could still track it to some degree. But it just looked like a small shooting star. Once it was deployed on its way to its final point, once it was released towards its final point, it needed to deploy. So as I mentioned, it was folded up to fit in the nose cone of the rocket that launched it. And it underwent a very nerve-wracking 2-week process of being unfolded, almost like a piece of origami, where the mirror had to fully deploy and the sun shield had to fully deploy. And I remember the launch. I was so nervous at the launch because, in the back of your head, you think, yes, it's strapped to the top of a big rocket. There's a tiny chance that the rocket could explode or fail or something, and, the telescope would be lost. But actually this process of deployment, it was equally nerve-wracking. And, you're looking here at all of the different bits that had to be unfolded. If any one of these small things goes wrong, if it doesn't deploy, if something breaks, if a latch doesn't release, if a latch doesn't close on the other side, you have a $10 billion piece of space junk. Okay, it's completely useless. And it had 340 or so of those single point failures. So if any one of those 340 single point failures occurred or happened, we didn't have a telescope. But it worked absolutely perfectly. The first stage of commissioning, so once it was launched, the mirrors needed to be aligned, which happened just over a year ago. And this is the very first engineering image, or mirror aligned engineering image taken. And it's just of a very boring star, but it's basically to show how sharp the images are. One thing that jumped out at me immediately in this image was not the star, because the star is just a boring star, but it's the amount of galaxies you see surrounding the star in the background. Because you have that big mirror, you're collecting so much light, you're seeing galaxies everywhere in the sky. Soon after this, we had alignment. We had the optimal alignment to focus the light onto all of the different detectors. So James Webb has 4 different instruments. These are the instruments just separated out. Once the telescope had reached this phase, it was time to commission the instruments themselves. Okay, so the mirror had been aligned. Now we needed to check out the instruments, and that's what I'm going to talk to you about in terms of Python. It's how we use Python to check the instruments, calibrate them, and the preparation as well. Okay, this is an example of just what the previous best view of the sky was on the left with the Spitzer telescope, and on the right is an image of the same patch of sky with James Webb. So it was really a massive leap forward. Of course, not many people saw the engineering images, or, you know, only really if you followed it. What people mostly are familiar with now from James Webb is images like this, which are spectacular and, you know, awe-inspiring and all of the rest of it. But this is not what an image, or this is not what the telescope sends back, which is the key thing. This takes a lot of processing, a lot of calibration, and a lot of understanding exactly what is happening in the telescope and the detector. So really, something like this is made up of individual panels, which start off their light as raw data telemetered from the telescope to the ground and formatted into some file structure. So a raw image looks something like on the left here, where you have you should be able to see kind of streaks up and across the detector, which are due to the, like, you know, noise and dark currents and so on in the detector pixels. You see spots everywhere, small kind of spots. These are cosmic rays that are striking the detector, which we're not interested in. You see kind of white patches, which are bad pixels. You see all sorts of crazy things down at the bottom left there. There's a streak of what looks like a flying saucer of weirdness, which we don't want either. So the purpose of calibration and what we were trying to do, and where Python comes into all of this, or in the work I did, was taking this image on the left, removing all the unwanted detector effects, because ultimately what a scientist wants is a picture of the sky, a science level picture of the sky, which only contains an image of what actually emitted the radiation, no detector effects whatsoever. So we start off on the left, we apply our knowledge and understanding of the telescope to remove those detector effects to produce one part of the overall mosaic. And then at a later stage, we combine all of the different panels to produce the large mosaics and to create 3-color images to produce the spectacular images you see in the media and the press releases. So how do we go from the left to the middle, I guess, is the main thing here. We want to take our raw data file, apply our understanding of the instruments to calibrate the image to produce a science level image, which is then mosaiced into the spectacular images. Well, the first thing we do is we need to understand our instrument. And previously, before launch, this was all based on ground testing. So on the top left there, you can see one of the instruments, our instrument MIRI, being loaded into a cryovac chamber, which kind of simulates the temperature and pressure in space. To do some testing on the detector. On the right is when the instrument has already been integrated into the telescope, and it's in the cryovac chamber A, I think, in NASA Johnson in Houston in Texas in the US. Which is a cryovac chamber that was used to train the astronauts who walked on the moon. And what all of this does is create space-like conditions, but then, you know, fire light onto the detector so we can see all of these different various detector and instrument effects that we need to remove. What we do then is we build up a series of steps that one by one goes through each of these detector effects or instrument effects that we want to take out of the image to produce the science level image that the scientists will use to do the groundbreaking research and win Nobel Prizes and so on. So from the ground testing, we already had a good idea, and this is an example of the first stage of calibration. We already had a good idea of going from the top, which is the raw data, which we call level 1B or a ramp file, going down through a sequence of steps, consecutively removing each individual detector effect or issue that we knew existed to produce something at the bottom that was almost science ready. Okay, this goes through another series of steps to make it science ready. And how you do this is key, okay, because this is an example of this, what we call a calibration pipeline for our instrument, okay? And it's no problem for us to write a calibration pipeline in Python or C or whatever we want to do. But because the telescope, so I'll just skip this one. This is the one I want to go to. Because the telescope has not just our instrument, but 4 instruments, each with a series of modes. Okay, so each instrument can do different things. We have 17 different science modes in total. That means that if you had 17 different teams of people working on 17 different calibration pipelines in 17 different languages, it becomes a mess. Okay. So the decision was taken, okay, we're not going to do that. And for example, something like this existed for the Hubble Space Telescope. There was different pipelines for different instruments, which were, you know, in different languages, which were just monolithic pieces of code that nobody could understand apart from the developers who developed them. And it became a bit kind of unmanageable. Hubble, of course, still does great things, but the decision was taken for Webb that they would move away from this model into some kind of common ground where all of the modes were written in the same language, using the same infrastructure, where the only difference was the pieces of code is somewhere in that infrastructure that applied to the specific instrument mode. Okay, and that's the JWST calibration pipeline. So it's a Python software suite. It has some C plugins where a bit more speed is needed, but the purpose of the calibration pipeline is that it will take raw data from any of those instrument modes, will use some internal logic to figure out which mode needs to be, or which instrument's being used, which mode is being used, which pipeline needs to be applied. Takes the raw data, moves it through the various stages of the calibration pipeline, and there are 3. The first is the detector 1, which is basically the kind of image I showed you a few moments ago, where you had the raw data being turned into some science level data. So that goes through detector 1, which just does detector level corrections and converts sort of an integration to a rate. The second level is instrument mode. And by the way, the first level applies to all JWST data. Every single instrument mode will go through that first stage. Second stage splits things out between spectroscopy and imaging or time series, where there's specific instrument mode calibrations, again, done all automatically using internal logic. The third is then when you have your science ready panes, for example, in your mosaic, and you want to combine them, you send them into the third level and it will produce the spectacular images that are released to the public. So this is the kind of overview of the calibration pipeline, a 3-stage process, moving through successive levels of calibration, going from pure raw data from the telescope to, you know, science ready data, which is then ingested into an archive where it's available for the scientists to use. This calibration pipeline was developed by a fantastic team of developers in the software science branch at the Space Telescope Science Institute in Baltimore, in Maryland, the USA. And it's openly developed on GitHub. So if you follow in the link there, you can go and download it and play with it and have a look at it. It's really an amazing piece of software. So why Python? I mean, you know, of all the languages, why was it Python that was chosen to do this kind of work? Well, there's many reasons. Okay, and the first reason that maybe a lot of people don't kind of think of, certainly in the astronomy community, is that the Python knowledge in the astronomy community is quite significant, because some of the libraries some of the Python libraries, like the array libraries and the science libraries and NumPy and SciPy, I mean, NumPy had its origins or part of its origins in astronomy, you know, in its early years. So those array libraries are perfectly suited to images and, you know, image processing and things like this. So all of this stuff already existed. So something like NumPy, SciPy, Matplotlib for plotting the images and the spectra and so on. You have things like Jupyter perfect for collaborative work in producing pipelines and showing off steps and all of this kind of stuff. You have AstroPy, which builds on all of those to produce an astronomy level, you know, a suite of astronomy specific tools. You have Sphinx and Read the Docs that are perfect to document all of this stuff. You have GitHub, where packages are openly developed, so everybody can go and have a look and contribute. And you have Anaconda, which will bundle them all up into a nice Python distribution, which you can easily install and have access to all of this stuff instantaneously. So it really is, the perfect language to write the JWST calibration pipeline. In addition just to the available software, you also, if you have experienced people who aren't developers, but say, oh, I think this could be improved for this reason, you can have input from the community, into the pipeline. They can make pull requests on GitHub to improve a step or a pipeline version or whatever. You have this constant improvement of the pipeline because it's out there and people can help develop it. It's very easy to maintain, which wouldn't be the case if there were 17 different pipelines with 17 different languages. It's developed in the open, as I already said. It can be very modular because of the way this is structured. So you can just slot steps in and out, change your pipeline around. You can do offline processing, which is very important for astronomers who want to fine tune the calibration parameters. Critically, it allows astronomers to focus on the data rather than the code infrastructure, because most astronomers aren't software developers, but they might know a bit of Python. But having a calibration pipeline with an infrastructure, which I'll show you in a minute, takes away the worry of handling file input, output, all of, reference file fetching, all of this other stuff, and allows them just to focus on the piece of code that will do the correction or calibration that they have come up with. Of course, it's free and there's no license required, which hasn't always been the case for astronomy software. And it integrates very, very nicely with post-pipeline processing. So once you have your science-ready products, you can use the suite of post-pipeline software, which is also written in Python. So, this is kind of an overview of why Python was chosen and just the power of Python for this kind of work. So just very quickly, just to give you an idea of what a file and an astronomy data file looks like. It's called, the standard is the FIT standard. It's called, means flexible image transport system. And what it is, what it is basically just a kind of a file with several extensions, where one of the extensions is the data extension, like is shown on the second from the top there, which holds your image. The primary header contains all of the metadata, like the date of your observation, the mode, the calibration software that was applied, all of this other kind of stuff. And in the other extensions, you can have stuff like pixel masks and other information that might be important to a user. But we want to take this now and put it in. So this is standard across all astronomy, but in terms of Python and the calibration pipeline, we want to parse this file and move it into what we call the JWST data model. So every type of file that the calibration pipeline uses has its own data model, and the data model is just an abstraction of the file. So it's a kind of a Python class held in memory that has attributes that correspond to the data extension, that correspond to the metadata, that correspond to the various other extensions in your file, which can be easily loaded into your Python code. And what it does is it buffers developers and users against changes in the file format, because every now and then new file formats will appear. But if your data model is perfectly capable of reading in different file formats, you remove the issue of having a user having to develop new code to read in the new file format, because the pipeline will do it automatically. Okay, so it's a very convenient tool to kind of take your real observational file, move it into memory, and then process it through your calibration pipeline. The pipeline backbone itself is based on what it's got on a module called ST-Pipe, which is Space Telescope Pipeline. I think it's a shortened version of that. It's a series of Python classes, and basically the smallest component is the Python step, or is the step class, the pipeline step class, and the step class is handles the processing of each individual calibration step will have its very own step class, which handles the movement, handles the input of the pre-calibration file and our data model, and the output of the post-calibration data model. And the data model is moved down through the series of steps with the calibrations applied in each of the step classes. And you can build up these step classes into what's called a pipeline class, which is your calibration pipeline. So instead of having to move through each individual class, you have a pipeline class, which is just composed of a series of steps. So you can send one file in to your class and it will put It will run it through all of these steps and output the calibrated file at the end. It also handles interface with the calibration reference system. So our understanding of the telescope is bundled, of the telescope and detector is, encoded in calibration files. So this SD pipe infrastructure will automatically understand what file it needs to fetch to perform the calibration, and handles all of that, again, taking all of that worry away from from astronomers or developers who are just working on specific parts of the calibration. Handles logging, all of the rest of that. So this is the backbone of the calibration pipeline. This is an example of what one of the steps looks like. So this is a step class called a fringe step, and you can see it just moves down, has some aliases, defines the reference file type, has a process method, takes the input, opens it as a data model, gets the reference file, does some logging, does some checks. The actual calibration is done in the sorry, you can't see my mouse, but a few lines up from the bottom, from the bottom, you will see output model is equal to fringe.do correction. That's the actual code that a developer or astronomer would work on to do the specific calibration, and you just slot it in here into the step class, and you don't have to worry about any of the input, output, or calibration file referencing or logging. Everything is handled by the SD pipe infrastructure. This is an example of a pipeline class where now you're taking a series of these type of calibration, of these type of step classes, and slotting them into a pipeline. So again, you're just defining the class. In this case, it's basically going through the flow diagram I already showed on the right. You define your step classes that are to be applied in this pipeline class. You go down into the process method. It does all of the stuff like fetching, reading the input into data model, skipping some steps if need be, checking the instrument mode, okay, because different instrument modes have different pipelines, and then applying the sequence of steps and producing the output. All of the different levels and different paths through this calibration pipeline are basically built around that same kind of structure. A series of steps, which are Python classes, and then a pipeline class for each of the green boxes here, which contain a series of those step classes. And that's how the data are produced. So basically on the bottom now is showing a real example, going from the left where you have some raw data, that, you have some raw data, but you have an image for every part of the mosaic, processing them all and then combining them into something at the end on the right. And this is the idea of the calibration pipeline, and very, very much rooted in Python. What about before launch? We needed to produce, it would have been great to be able to point JWST at the sky when it was on the ground, but of course it would never work. So before that, we needed to know what the sky could look like with JWST and create some test data so we could create all of the tests and the checks and all of the other things we did during commissioning. So during the instrument commissioning phase, to make sure everything worked fine, that the instruments were ready to do the groundbreaking science. How you do that is basically build a simulator. Okay, so you build an observation simulator that replicates what JWST might see in orbit based on our understanding of it on the ground. If you think about what a simulator is just taking a picture of the sky, what you think the sky looks like, and rather than calibrating out all of the things like in the pipeline, like in the flow diagram on the right, you just turn those arrows around. You start off with a picture of the sky and you successively add all of these effects back in. And that will give you the simulated raw data. Okay, so now you have a starting point, and you can, and indeed you can use this to test the calibration pipeline, because it's just the inverse. So if you create a good simulator, and then run the output through the pipeline, it should remove all of the effects that you've put in. Okay, so there's lots of different uses for this. Our simulator that we developed was for the MIRI instrument, which is the one we worked on here. And MIRI, because the pipeline was being developed in Python, and because there's so much experience of Python in the community, of course, we wanted to do the simulators in Python. So our simulator was called MIRI Sim, and it was a Python package developed to simulate observations, including various instrument effects through MIRI. We used our knowledge of, from ground testing, which is encoded in the calibration data products, to add all of those effects back into an idealized picture of the sky. And all of the outputs and everything were in the same format as expected by the calibration pipeline as input. So basically the raw data file that I showed you, the FITS file, is output by our simulator so that it can be just ingested straight away through the pipeline. And what we were doing basically is taking an idealized picture of the sky on the left, either through a real image or, built up through a sequence of additions of diffuse emission and point sources. We basically put that through the telescope system to give something like is in the middle, and then we start adding all of the detector effects to give something like on the right. This is extremely useful, which I'll go through in a minute. I basically just said all this, so I won't go through it. But it was a very, very good simulator. So what we have here is just a built-up synthetic sky, four panes on the sky, because we wanted to check the kind of dithering process as well, which is done in real observations. We had a bunch of point sources, 2 galaxies, and we saw that simulating them and putting them through the pipeline goes from all of the the raw image format with all of the detector effects into a very nice mosaic of the sky. This was used extensively to generate data for the commission analysis tool developing and testing, which I've already mentioned. So this was a very nice image we produced during commissioning last year, because one of these is an image I created for our testing purposes to test our commissioning tools. And the other one is the actual observation that was taken during commissioning, which we wanted to apply our tools to. And you can see that unless you really knew what you were looking for, you can't tell the two of them apart. Okay, the real one is the one on the right, because those 3 panes that look a little bit different have an additional component in the light path. But unless you knew what you were looking at, there's no way you'd be able to tell which one was synthetic and which one was the real observation. So it was a very, very powerful tool for us. Again, all developed in Python using very similar step classes like with the pipeline, just in reverse. So this is our commissioning team who used the simulators and the pipeline to do all of the checks of all of our instrument modes on MIRI, but there were similar teams for each of the 4 instruments on James Webb. So these are all the instrument modes, and we had to go through science readiness for checks on these specific dates. And on the 8th of June last year, the nearest, or was it the 16th of June last year? No, in June last year, I can't see the dates. In June last year, we had the final check, which is when the telescope was officially signed off as ready for use. And soon after, we had the very first release of science data, and it was released in a ceremony by President Joe Biden in the US, who showed the very first science release image with JWST, because of course we'd been commissioning the telescope for months, and we had plenty of images before this, but this was the first one that was released to the public. At that time, a few more images were released. So we had the beautiful, the kind of beautiful press release with the beautiful objects, all of which are related to the science teams I discussed at the start. So the bottom left is the assembly of galaxies. It's an image of Stefan's quintet, which is a series of interacting galaxies. The top right is in the Carina star forming region. So it's in something like this that our star and our solar system would have formed. On the top left is what our solar system will look like in about 5 billion years. It's a planetary nebula. So just to give you some idea of scale in the planetary nebula there, if you look at on the very left image on the top left, in that blue region, our entire solar system would fit very, very nicely in there. So at some point, the sun is going to shed its outer layers and blow through the solar system. And the bottom right is the image that was released by President Joe Biden. And this is called the JWST first deep field. So this was when the telescope just stared at a patch of sky for an extended period of time and looked back through the universe at very, very distant objects. So in this image, there's some small red dots clumped around. These are some of the most distant galaxies that have ever been observed in the infrared. Okay, and it took JWST 1 night to do that, which is insane, because the telescope is going to be doing this all the time, looking at the same patch of sky, creating ultra deep fields, and looking at the very, very first stars and galaxies in the universe. Here's another. So this is the first deep field. Here is one that's come out since. This is an observation of a galaxy cluster called Able 2744 with the Hubble Space Telescope. And there was maybe 1,000 galaxies in this image. But again, a very quick observation, which AWST produced something that looked like this, which has 10,000 galaxies or so in it. So you can really see the power and kind of multi-generational leap forward in capability to observe the sky that was introduced by this telescope. And remember, images like the one you're looking at now were produced by putting the raw data through the Python code, through the pipeline, through the post-pipeline processing tools, all developed in Python. And I think it shows the the importance of Python and the power of Python in the work we're doing with AWST. So I go through some of the highlights since. So I mean, this was this is the Carina star forming regions, which I just mentioned. So as I said, solar systems like our own would have formed in here. So along the ridge here, if you could zoom into some of these protrusions that are sticking out, you would get something that looks like this. And these are the pillars of creation observed with AWST. And if you look at the densest, darkest regions to the right of the pillars, you will see at the edge of a lot of them, there's a bright red source. Okay, that bright red source is a young sun forming. Okay, so this is exactly how our sun formed in something that looked very, very similar to this. And JWST allows us to peer through that kind of dark gas and dust to look right at the very start of the star formation process and planet formation process, which wasn't possible with Hubble because it couldn't see through the gas and dust. But now we can look right in and see what's happening. Here's an example of what a zoom in of one of those would look like. Okay, and again, this is a picture of the sun 5 or 6 billion years ago. Right, this is kind of exactly what our solar system looked like 5 billion years ago, where you have the sun still forming in the middle, still gathering mass from, I'm sure you can see the kind of dark streak across the middle there. That's the accretion disk. So it's accumulating gas and dust from the accretion disk. The star is still growing. It's creating these outflow cavities above and below. It's in a disk like this that the Earth and the planets formed. So it's just amazing to think that you're looking into something like this now. And basically everything that humanity knows, all invention and creation and knowledge and everything originated in some swirly vortex of gas and dust around a forming star 5 billion years ago. But there you go. If you could zoom out and look at a very large star forming region and something like this is NGC 346 in the Small Magellanic Cloud. This is what star forming regions would have looked like in the very early universe. And if you could zoom, these are enormous now, but if you could zoom in on some small parts of this, you would see something like the images I just showed. So a star cluster or cluster forming region like this will create tens of thousands of suns. We can see the endpoints of stellar evolution. So this is a very, very evolved star. So this is a star that's just about to go supernova, which I said, when I say just about to go supernova, it could still be 100,000 years away, but it's just at the end point of its life. We can also see what it would look like if it exploded. So this is looking at a stellar explosion in another part of the sky. This is a supernova remnant called Cas-A, and it's the remnant of it's the debris of an explosion that happened about 300 or 400 years ago. And this was a naked eye supernova. This was observed in the sky and recorded in history as being a new star in the sky, which was visible for a certain period of time. You can look back on it now with modern telescopes and see something like this. And what you're looking at is the metals and dust. So cosmic dust basically gets formed in these explosions, which is distributed into the interstellar medium, which then goes into new generations of star formation. So it's in something like this that the metals that are in our bodies would have been formed. We can look at galaxies nearby and see basically the skeleton structure of the galaxies. So all of this white stuff here is gas and dust around the galaxies from which stars are born. In the middle of the two, of the bottom and the right galaxy, you can see the supermassive black hole as the bright source in the middle. You're looking at emission coming from around the black hole. You can see galaxy mergers. Okay, so you can see gas and dust being just thrown everywhere as two galaxies collide head on. In this image, we've been able to observe some planets, not only in our solar system, like Uranus on the top left and Jupiter on the top right, but we've been able to image exoplanets around other stars, like along the bottom left. Okay, they don't look as spectacular as Jupiter or Uranus, but you can tell an awful lot about those planets by looking at these kind of images. You can try, if you monitor them in time, you can tell if they have seasons or weather or rings or stuff like this. Okay, so you can do an awful lot of science with that. We can look at the effect of planets moving across the face of their host stars to see the dips. This is also very useful because if you do this with some of Webb's most powerful instruments, you can measure what's in those atmospheres. And this has been done a few times already. And we're like, you know, as the year goes on, we will see more and more of this kind of thing. But in this, this is a super Neptune, I think, WASP 96b, where lots and lots of water vapor was detected in the atmosphere. So basically steam in the atmosphere. It's very, very close to its host star, so water can't exist in liquid form. We could also measure lots of carbon dioxide in this exoplanet, WASP 39b, which again, I don't think was expected to have so much. So it was just a straightforward measurement, but it had already had implications for the understanding of these types of objects. And this is my favorite image still, taken by Webb. And it's the image I'll leave you with, because I think this very nicely shows off the capabilities of Webb, the capabilities of the telescope, and what potentially we'll get in the future from it. Because it's looking at a patch of sky with a planet that you're all familiar with called Neptune, which looks like this glowing pearl sitting on a black backdrop. But you can see Neptune's dusty rings. You can see kind of the clouds moving across Neptune's surface. You can see the bright source to the top left of Neptune is its moon, Triton. But around Neptune, you can see distant galaxies, and you can see all of those small red clumps that are basically, you're looking back through the universe, to the earliest stages in the universe. So in one image, we have something on our doorstep like Neptune and Triton. We have something that's more nearby, like some of the stars. We have the galaxy in the bottom left, which is a nearby galaxy, but then you're looking all the way back through the universe. So I think this image encapsulates everything the telescope is about. And this image would not be possible without all of the work and the development that went into producing things like the JWST calibration pipeline and the simulators that we use to commission the instruments in the telescope. So I think I'll leave you with that, and I hope you enjoyed my talk. So I guess the floor is open for questions now. Thanks very much.
Thanks, Patrick. That was actually a truly fascinating session. It was really, really interesting to see you dive into the universe and how we continue to make steps to discover even more of it. We actually have got quite a few questions that have come in, some interesting questions actually. So we'll start with, why are the black holes so bright? Aren't they supposed to absorb light?
Yeah, so what you're seeing there is not the black hole itself. You're seeing material around the black hole. So yeah, you're absolutely right. No light can escape the event horizon of a black hole, but what you absolutely can see is what's happening around the black hole. And because a supermassive black hole is an enormous source of energy, okay, so the material that's, let's say, in the accretion disk around the black hole, so spiraling around, will be visible in various types of light. The system will also have this like donut-shaped gas and dust structure nearby, which is also visible. You will have lots of reflection of this light all around the place. You could have jets of being emitted from in and around the black hole region. There's lots you can observe from near a black hole, but you can never see light that's coming from the black hole, let's say. Yeah.
Okay. The next question is, how is the distance to galaxies calculated from these images?
From the images, it's not really done from the images. It's done from, you can do it from images, but there's still some uncertainty. Usually what you do is you do spectroscopy. So you will look at the spectrum of the galaxy, and you will see, for those who maybe aren't familiar with a spectrum, but you will see, let's say, a continuum of light, okay? So going from like red light to blue light, say it's a continuum, so it's a flat line, but across that flat line, for argument's sake, say it's a flat line, across that flat line, you will have emission lines or absorption lines, which are due to some of the elements which are in there, okay? So hydrogen is abundant in the universe. So let's say you have an emission line due to hydrogen. Those emission line wavelengths are very well known. If you observe a galaxy, the galaxy is very, very far away, and it's moving away from you because of the expansion of the universe. So that line will actually move, because the light coming from the galaxy would be redshifted because the light has to travel across an expanding universe. So based on where you would expect that light in your rest frame to where you measure it coming from the galaxy, you can work out the distance to the galaxy very, very accurately.
Right. Another question is, why do we have to launch the telescope out to space? Won't the same pipeline work for images taken from Earth?
Oh, it was a very good question. Yeah, one of the reason you have to go to space is we're observing infrared light. Okay, so infrared light, as I said, is heat radiation. If you put something like JWST on the ground and point it at the sky, it would be like trying to see a great example, or a great analogy for it is if you're standing in the middle of, what's the biggest sport in Sri Lanka? Is it cricket?
Yeah.
All right. So let's say you stand in the middle of your biggest stadium at nighttime, and all of the floodlights are shining down onto the pitch, and you try to look up to see stars in the sky. You're never going to see them, right? Because the floodlights are just blinding you to the faint objects. It would be the very same thing for James Webb. The atmosphere itself will be emitting the same radiation that you're trying to detect. So you would be just looking up and lose everything in the light coming from the atmosphere, because the atmosphere is warm, right? So you wouldn't see anything. So for this reason, and even as well, because you're looking at infrared radiation, the telescope would be warm. So the telescope would be emitting the light. The mirror would be emitting the same light you're trying to detect. So for these reasons, you need to move it into space where everything is cold. The only thing you have to grapple with in space is the sun, which is why that big shield sits under the telescope. It is always pointed at the sun and kind of keeps the telescope cold enough so that it can see the infrared light coming from the distant universe.
Okay. And I think we have actually a couple more that have come in. Yeah, another one is like identifying components in faraway planets. Can we identify what are the constituents of the dark matter and its effects through the same Python abilities?
True. Well, I'm not sure of any specific searches for dark matter with the telescope. Dark matter, I don't think it's designed for it, to be honest. I'm no expert in dark matter, so James Webb itself is not the type of telescope that would specifically search for dark matter. Well, to look for dark matter, you need something like a survey telescope, and I think there is one due to be launched either this year or next year called, I can't remember what it's called. But it's also an infrared telescope, but it will survey the sky looking for signatures of dark matter. But Webb itself is not that kind of it's not that kind of telescope. It's more designed to look at very interesting things in fine detail. Something like dark matter, you need a survey of the sky to try pick out signatures of it, because it's not concentrated. You know, it's very diffuse in the sky.
Okay. The last question is any of this pipeline code available open source?
It's all open source. Yeah, it's completely open source. So it's developed. So on one of the slides I showed it, you know, it's developed openly on Python. You can just go search JWST Calibration Pipeline. You will find the Readiness page, the GitHub repo. You can go and download it, play with it. There's already been there's been other, so the same pipeline will also be used for the next big NASA mission, which is the Roman Space Telescope, which will be launched, I think, in 3 or 4 years, or maybe a bit more. But I mean, that pipeline infrastructure is designed to be very generic. Okay, that the same code can just be used on any pipeline for any telescope. You just need to slot in the different calibration specific code lines. The infrastructure will look after everything else with input, output, calibration files, all the rest of it. So yeah, it's completely open source and it's designed to be usable by other telescopes. There has been efforts to adapt it to, or to use it for optical telescopes on the ground as well. I don't know what the status of those is though.
Okay, so I think that concludes our Q&A session. Of course, if there's anyone else who would like to drop in a very quick question for Dr. Patrick to ask, you're more than welcome to. You can drop it into the Q&A box. But if not, it's pretty fascinating to see that there has been such a connection between the cosmos and the part that Python has played in its continued discovery. So thank you, Dr. Patrick, for a riveting session to close off the evening. We hope that you all have found today's sessions inspirational, and we thank you for joining us today for PyCon 2023. A massive thank you goes out to Matifique and to all the relentless hard workers behind the curtains who've done a tremendous job to pull this off. Of course, we can't forget the panel of incredible speakers who've gone above and beyond, and in Dr. Patrick's case, to space as well, to craft some truly spectacular sessions. We hope to see you all again next year, but until then, have a very good evening, and thank you for tuning in to PyCon 2023.